All right, welcome back. Today we are jumping into a big one from university level calculus, something that can really throw you for a loop, finding area with polar coordinates. If you've ever stared at a beautiful shape like a cardioid or a rose curve and thought, how on earth do I find the area of that? Well, you're in the right place. Let's get into it. So, you're probably a pro at finding area the old-fashioned way, right? In Cartesian coordinates. You just sum up a bunch of super thin vertical rectangles moving from left to right. Well, for polar coordinates, I need you to throw that idea out the window. We have to completely change how we think. Instead of scanning left to right, we're going to think like a radar, sweeping around a central point. We're not adding up rectangles. We're adding up these little pie pieces, these radial wedges. And it makes perfect sense, because our radius, r, is a function of the angle, theta. So our building block should be based on a tiny change in that angle. It's a total shift from thinking in lines to thinking in circles. And that brings us right to our first big idea, really understanding this new building block for area. So yeah, forget rectangles. Our new go-to shape is the circular sector. And honestly, the best way to picture this? It's just a tiny slice of pizza. I'm serious. Every slice has a certain length, that's our radius, r, and it takes up a tiny, tiny angle, which we'll call d theta. Our whole strategy is just going to be adding up an infinite number of these little pizza slices to get the total area.
Okay, so if we're adding up an infinite number of tiny things, that should sound familiar, right? That's an integral. This idea of summing up all those little sectors leads us straight to the formula we need. This is our essential tool.
And here it is, the big one. The area, A, is the integral from some starting angle alpha to some ending angle beta. And what are we integrating? It's 1/2 times r squared d theta. Let's break that down. For every tiny slice defined by d theta, its area is 1/2 r squared. The integral sign just means we're adding all of those slices up between our start and end angles. That's it. Now, a formula is great, but how do we actually use it? Well, it's a simple 3-step game plan. Seriously, if you do these 3 things every time, you'll be golden. First, you have to sketch the curve. You need to see the area you're trying to find. Second, you find your bounds. Where does the sweep start and where does it stop? And third, you just plug your radius function and those bounds into the formula and solve. Let's see it in action. Okay, let's put this process to the test. We're going to start with a classic shape you will absolutely see in your calculus course, the cardioid. So here's our mission. Find the total area inside the cardioid defined by r equals 1 plus cos theta. And you can see why they call it that, right? It's literally a heart shape. So how do we do it? Let's follow the steps. 1 and 2 are sketching and finding the bounds. Now, if you trace this thing out, you'll see that the entire heart shape gets drawn exactly 1 time as your angle, theta, goes all the way around the circle, from 0 to 2 pi. So, boom, our bounds are set. Alpha is 0, beta is 2 pi. Done. Now, for step 3, we just set up the integral. We plug everything we have into the formula. The area is 1/2 times the integral from 0 to 2 pi of our radius, which is 1 plus cos theta, squared. Now, to actually solve this, you're going to have to dig into your calculus toolbox and pull out that power-reducing identity for cosine squared. You remember that one, I'm sure. And after you crunch through the calculus, what do you get? 3 pi over 2. That's the area. It's such a clean, nice answer, right? And it just perfectly shows how our simple 3-step process can take a weird-looking polar curve and give us a concrete, simple area. Okay, that was the warm-up, finding the area of a whole shape. But you know, exams, they love to throw curveballs. So let's level up and talk about the trickier problems, like finding the area of just one loop of a curve, or the space between 2 curves. This is a perfect example. The function r equals 4 cosine of 2 theta gives you this awesome 4-petaled rose. But what if the question isn't for the whole flower, but just for the area of one single petal? How does that change our game plan? Here's the key trick. To find the bounds for just one loop, you have to ask yourself, where does the petal begin and end? Well, it starts and ends right at the center, the origin, which is where the radius is 0. So the technique is to just set r equal to 0 and solve for theta. For this curve, that gives us bounds of negative pi over 4 to positive pi over 4. Those are the start and end angles for one petal. So we use those new bounds in our integral from negative pi over 4 to pi over 4 and solve it. The result? The area of that one petal is 2 pi. See how that works? It's all about finding the right bounds to isolate the exact piece of the curve you care about. All right, you ready for the final boss? This is the kind of problem that shows up on final exams to really test your understanding. We want the area that's inside the circle but outside the cardioid. We're looking for the area trapped in that gap between them. Now, the logic here is actually pretty similar to what you've done before in Cartesian coordinates. You're going to take the area of the outer curve and subtract the area of the inner curve. That all gets combined into one integral. It's 1/2 times the integral of the outer radius squared minus the inner radius squared. And how do we find the bounds? Well, we need to find where the two curves cross paths, so you set their equations equal to each other and solve. Okay, stop. I need you to listen very carefully. This is the single biggest mistake students make on these problems, and I want you to avoid it. Do not subtract the two radii from each other and then square the result. That is completely wrong. You have to square each radius individually first and then subtract them. It's the difference of the squares. Please burn that into your brain.
Whew, okay, that was a lot. We went all the way from the basic concept to some pretty tough exam problems. So to make sure this all sticks, let's just boil it all down to a final checklist. Here are the 5 rules to live by. 1. Always sketch it first. You have to see what you're working with. 2. For a single loop, find your bounds by setting r equal to 0. 3. For the area between curves, find your bounds by finding where they intersect. 4. Don't you dare forget that 1/2 in the formula. And 5, the big one we just talked about, you subtract the squares of the radii. This checklist right here is your key to getting these problems right every single time.
So think about what we just did. We took these beautiful, complicated curves that would be an absolute nightmare to handle with x and y, and by just shifting our perspective, by thinking in circles instead of squares, we made the problem totally solvable. It really makes you wonder, doesn't it? What other complex problems, in math, in science, wherever, are just waiting for us to find a new perspective to unlock them?